So having seen some of the applications that we can achieve using BFS and DFS, let's go back a little bit and look at the connection between BFS and DFS and these representations that we talked about, adjacency matrices and adjacency lists. So let's just formally remember what BFS does. So BFS explores a graph level by level. So we maintain two pieces of information. We maintain this flag called visited, which indicates whether a vertex has been visited or not. And we keep this queue of unexplored vertices. So initially we mark all vertices as unvisited. We start from a vertex j. So we start by setting that to be visited, set its value of visited to true, add j to the queue, and then we repeatedly process the queue. And by processing the queue, what we mean is we take out the first element in the queue, look at its neighbors, and if there is any neighbor which is unvisited, we mark it as visited and push that neighbor back into the queue. So it will get processed later on. And finally, when the queue gets empty, BFS terminates. On the other hand, with depth first search, we do a kind of aggressive or impatient traversal. So we start with I and we visit one neighbor j. And now once we visited one neighbor j, instead of going back to I and continuing with another neighbor of I, we suspend I and we go to neighbors of j. And the first time we find a neighbor of j, again we'll suspend j and go to a neighbor, that neighbor k, and continue, right? And at this point when we finish and we can't go further, we go back and then we traverse back all these suspended vertices until we find one which is not finished and look for another neighbor and so on. So here we keep track of this visited information like in BFS, but we also have the stack which remembers the suspended vertices, so we can go back in the correct sequence, last in, first out. So what I want to talk about is how much time this takes as a function of the size of the graph that we're trying to explore. So typically in a graph there are two parts. There is the vertex set and there is the edge set, which is a subset of the pairs of vertices, right? So edge relation is a subset of V cross V. Now the vertex set is usually denoted as having size n. Okay, so this tells you how many nodes or vertices there are in the graph. Now with the same set of vertices, you can draw many edges or you can draw few edges. So actually the parameter of the number of edges is independent in a sense as a measure of how complicated the graph is. So this is usually denoted by a small m. So m is usually the number of edges, n is the number of vertices. So we saw that if you have a tree that is a minimally connected graph, then you will have n minus 1 edges. So we can have interesting graphs in which the number of edges is roughly the same as the number of vertices. You have n vertices, you have n minus 1 edges. On the other hand, if you connect everything to everything, then for every pair of vertices you have an edge, and this gives us n into n minus 1 by 2, which is n choose 2 vertices, right? So this is about n squared, right? So something like n squared. So we can have either order n vertices or order n squared vertices. So therefore the number of edges, so the number of edges forms a somewhat independent parameter in our calculation. So now let's look at both BFS and DFS and see how they do this, right? So the first thing is that they visit and explore every vertex exactly once. That's the purpose of that flag visited. It makes sure that we never go back to a vertex which is already visited and try to visit it a second time. So therefore we will visit and explore each vertex exactly once. So that whole thing happens n times. There are n times when we visit and explore vertices. Now what does exploring a vertex mean? Exploring a vertex essentially means looking at all its neighbors. So if we are looking at all the neighbors of a vertex, we are looking at all the edges which are outgoing from that vertex, right? So the question is, how long does it take us to do this when we are actually doing it computationally, not doing it by looking at the picture and doing it by hand? So we said that there are two representations that we have of the graph. The first is this adjacency matrix. In the adjacency matrix, the entries are 0, 1, and the ijth entry indicates whether there is an edge from vertex I to vertex j. So if there is an edge, it's 1. If there is no edge, it's 0. So if we want to look at the outgoing edges of a vertex I, the only way we can do it in an adjacency matrix is to walk down the entire row for I. So these are all, so you look at I comma 1, I comma 2, I comma 3 and so on up to I comma 0, I comma 1 up to I comma n minus 1, if the vertices are numbered 0 to n minus 1. So we will have to look up the entire row, so whether or not I has many neighbors or few neighbors or no neighbors at all. I mean, of course, in an undirected graph, it must have at least, if we had reached I during this thing, it would have an incoming thing, so at least one neighbor. But if it's a disconnected vertex from where we are starting, like we saw a component which has only a single vertex, then it may have nothing at all. But we won't know that until we see the entire row for I. So regardless of how many neighbors I actually has, we have to spend time proportional to n to discover all these neighbors, right? So this means that I have overall I'm processing n vertices, and for each vertex I have to scan n entries in this matrix. So n times n, so I have to do something proportional to n squared in order to do depth first search or breadth first search. On the other hand, if I use an adjacency list, then I have for each vertex an explicit list of its neighbors. So if it has a lot of neighbors, that list will be long. If it has very few neighbors, that list will be short. But I will spend no more and no less time than I need to scan this list, right? So if I have k neighbors, I have to look at k entries, but I don't need to spend more. I don't need to spend n steps looking for k entries when k is small. Now the problem with this is that the degree of the vertex, as we call it, right? The degree is the number of vertices which are number of edges which are incident at a vertex. The degree of a vertex varies, right? So maybe for vertex 1 I had a small degree, vertex 2 I had a big degree, and so on. So if I want to count how many steps it takes across these n vertices, I have to add up the degrees, right? I have to look at how much time it takes for degree 1, how much time it took for degree 2, and so on. So how do I get a good way of estimating what this adds up to, right? So the question is, when I'm processing an adjacency list, I do work proportional to degree of each vertex added up. When I process vertex 0, I will look at all its neighbors, so I will spend time proportional to degree of 0. When I do vertex 1, the same thing, vertex I, the same thing, right? So we are really interested in identifying what the sum of the degrees in an undirected graph represents. So what is a degree? A degree indicates a number which is the number of things going out. So if I have I, then if I have so many things going out, then I get a contribution of 4 from I to the sum of the degrees, because it has 4 outgoing things. But each of these things will go and terminate also in j. So if I look at this edge I comma j, right, it adds 1 to the degree of I, it also adds 1 to the degree of j. So each edge contributes to degree of both I and j, right? And every number that I get in the degree must come from some edge. So since there are m edges, right, and each edge contributes to the degree count of both the starting point and the ending point, the sum of the degrees must actually be 2 times m, right? For each vertex, each edge 1 to m, it contributes 1 plus 1, right? So it's 2 times m. So now we can see that if you have BFS or DFS with an adjacency list, then you make n steps, you take n steps to visit each vertex, and then across the n vertices, you take the sum of the degrees, or 2m steps, to explore all of them, right? So this says that the time that overall that you spend is proportional to n plus m. You have to visit all the vertices, because for instance, if the entire graph is disconnected, right, if there are no edges at all, m is 0, but it doesn't mean that you will finish your DFS or BFS in 0 time. You have to visit all the n things. So you have to spend n steps looking at all the vertices, and across the vertices, the contribution of that vertex to your work is the degree of that vertex. So across the vertices, it's the summation of the degrees. That's where this m term comes. Whereas, as we saw, if you did this with an adjacency matrix, it doesn't matter really what the degrees are and what m is. You will end up having to spend n steps for every vertex, because you cannot find out the neighbors of a vertex without looking at the entire row. So you end up taking time n squared. So the real distinction is between n squared and n plus m, right? So we said that m could be small. So m could be like n, like in a tree, we have only n minus 1 vertices, or m could be large. It could in principle be n squared. If it is n squared, then these two are roughly the same. But if it is small, then we have a difference between something which is proportional to n and something which is proportional to n squared, and that's why adjacency lists can be beneficial for doing our thing, right? So if m is proportional to n, then we have a big saving by using adjacency list representations. So though adjacency matrix is fine in terms of understanding what's going on in terms of mechanically computing something, it can actually cost us, not just because it's a large thing and we are keeping a lot of zeros in it, but also because in order to extract this interesting information about what are the neighbors, we have no better way than to walk down the entire row. So here are some more interesting things that it's useful to remember about degrees. So remember that the degree of a vertex can be obtained from an adjacency matrix by just looking at its row. So if you just count the number of ones in the adjacency matrix in a row, you get the degree of the vertex. And if it's an undirected graph, right, you can also get it from the columns, because the number of incoming edges and the number of outgoing edges is the same because it's a symmetric kind of edge graph. And if we have an adjacency list, then the degree is just the length of the list associated with I. It's all the neighbors of I. Now we already calculated that the sum of the degrees is 2m. So 2 times anything must be an even number. Okay, so the sum is an even number because it's 2 times the number of edges. So the number of edges themselves will be odd, but the sum of the degrees is going to be 2 times m, and therefore the sum of the degrees is an even number. Right? So now you should remember that if you have an odd number plus an odd number, then I'll get an even number, right? So for example, if I do 3 plus 17, then I get 20. But if I do an odd number plus an even number, then I get an odd number, right? So you can think of the fact that if I'm pairing up an odd number in 2's, then I get one leftover element. That's why it's odd. And if I'm pairing up an even number in 2's, I get no leftover element. So if I take them together and pair it off in 2's, then I have one leftover element. That's why it's odd. Whereas if I have 2 odd numbers, then each of them contributes one leftover element. I can take those leftover elements and pair them up and I get a new pair, and so it's even. Right? So odd plus odd is even, odd plus even is odd. So this means that if I spot an odd degree vertex in my graph, it cannot be the only one. There must be another one. Right? Because otherwise the sum of the degrees will become odd. Everything else is even plus one odd number will be an odd number. So if there is one odd number here, there must be an odd number somewhere else. So I can pair them off. Similarly, if I find a third odd vertex, there must be a fourth odd vertex. Right? So for every odd degree vertex, there must be another odd degree vertex. Right? So in other words, the number of degrees odd degree vertices must themselves be even. Right? If I have an odd number of vertices with odd degree, then the overall sum of the degrees will be odd, which is not possible. So remember also that the degree of a vertex can be any number between 0 and n minus 1. Right? So 0 happens when this vertex is actually disconnected from the entire graph. N minus 1 happens when it is connected to every one of the remaining n minus 1 vertices. So it's not connected to itself, obviously. We said no self loops, but it could be connected to everything else. So the special case where every vertex is connected to every other vertex is what is called a complete graph. So for instance, on a 3 vertex graph, a complete graph is just a triangle. For if a 4 vertex graph, then I must connect everything to everything. So I have a square and then I also have the diagonals, right? Similarly, if I have a 5 vertex graph, then I will have a pentagon with all these diagonal things. Right? So this is what is called a complete graph. So in a complete graph, the degree of every vertex is n minus 1, and I will actually have n into n minus 1 by 2 because every pair is connected. So I have n choose 2 edges. Now in many graphs that we encounter in practical problems like the ones we discussed about graph coloring or vertex cover and so on, in many reasonable situations you can actually say that a particular node will have no more than a certain number of neighbors. For example, remember the graph coloring problem for the security cameras. So clearly if I give you a particular building, right, then I know that a given intersection will not have more than a certain number of corridors fixed. I cannot have a large number of corridors at some point, right? So there will be some upper bound saying that no corridor, no intersection has more than 5 corridors which meet there, right? Or if we are looking at some other problem which is say for instance placing ambulances at an intersection, then you want to know how many roads meet at that intersection. Or if you are looking at say the timetabling problem, you want to know how many different courses can be scheduled in the same slot. Now obviously if you have a fixed number of courses in your curriculum, not more than that many can be there, right? So very often the degree is actually independently bounded by some number. You don't have arbitrarily large degree. So the degree is bounded by an external constraint. And if you have now a constraint on the degree, it says that each degree is k, then the total sum of the degrees can be at most k times the number of vertices, k times n. And since this is twice the number of edges, the number of edges must be k times n by 2. So in other words, if you have a bounded degree graph, where every edge has a bounded degree which is independent of the size of the graph, then the total number of edges cannot be more than linear, cannot be more than some function of n. So therefore, you should be working with adjacency lists. And finally, if you have directed graphs, we said that it's no longer enough to talk about degree, because there are edges coming in and there are edges going out which are quite independent of each other. So we must talk about the in degree and the out degree. So in this case, because each edge contributes to one in degree and one out degree, the sum of the in degrees is the number of edges, and the sum of the out degrees is also the number of edges. So together the in degrees plus the out degrees is 2m, but they get partitioned into two quantities which add up to m each. Right? So what we have seen is that if we do an analysis of how the BFS and DFS work with respect to exploring the neighbors of a vertex, if we use an adjacency matrix, it turns out that regardless of how many neighbors a vertex has, we must scan the entire row, and therefore the time taken by BFS and DFS becomes proportional to n times n. I have to process n vertices, and for each vertex I have to scan n elements in that row. On the other hand, if we use an adjacency list, then the time taken to process a vertex is exactly the number of neighbors it has. So it's across the vertices is the sum of the degrees, and this gives us an overall timing which is proportional to n plus m. And we also saw that there is a large variation in m. So m can be linear like in a tree, or it could be quadratic like in a complete graph. So it's important to be able to distinguish and use the appropriate representation, in particular use adjacency list whenever we can. Right? Another situation where we get small number of edges is when we have a bounded degree. So if we have some other constraints on our problem which says that the number of edges coming out of a given node cannot be more than a certain number independent of the total number of edges, right? Then we have necessarily a graph which has only a linear number of edges. So again, an adjacency list matrix representation would work best.